Unit 2.2 is all about capacitance, and the first question from the quiz on Unit 2.2 was a circuit that has a network of capacitors in combinations of series and parallel. And we have to find what's the electric potential difference between point X and Y. In other words, what's the value of Vxy? We notice that this point X is at the same electric potential as this point that I might call B. And if I want to, I could put the symbol for ground right here. So we know the electric potential at point X, at point B, at this point, in fact, at the lower plate of capacitor labeled as C, is a value of 0. So if I could find the potential difference across the 15 millifarad capacitor, that would give me the electric potential at point Y. We know the electric potential at point X is 0. So really that's all we're trying to find. When we say, what's the potential difference between points X and Y? We can extend point X to here, and basically point X is the electric potential at the lower plate of the 15 millifarad capacitor, and point Y is the potential at the upper plate. So yeah, what's the potential difference across this capacitor? Let's see if we can draw this circuit in a simpler way. I've got these points A and B, and we've already identified an X and a Y. Let me put another point right here, maybe call it C. Actually, A, B, and C aren't convenient because that's the letters I chose to label these capacitors. So change the nomenclature just a little bit. Maybe just call this point 1, point 2, and point 3. So starting at point 1 and going to point 2, we encounter 20 millifarads of capacitance. And that gets us from point 1 to point 2. Now, to get from point 2 to point 3, there's two paths we can take. One path encounters capacitor B and C. The other path that gets us from point 2 to point 3 just encounters this one capacitor. So this is a way to say that we have a parallel combination. And on one path, we just see this 24 millifarads. And on the other path, we see both a 10 and a 15 millifarad capacitor. Okay, so then that gets us to this point 3. Of course, to get from point 1 to point 3, we didn't have to go through all this combination of the 20 connected in series with the 10 and 15 in series, which is in parallel with the 24, yada, yada, yada. The easiest way to get from point 1 to 3 is just to go over that branch, right, from 1 to 3. And that way, we would just encounter 8 millifarads of capacitance. So this is another way to diagram the whole circuit. Now let's see. We're going to use the rules for combining values, and the first combination we can make is the 10 and 15 together. Now, when capacitors are in series, we can use that product over the sum rule. We can say 10 times 15 over 10 plus 15, or 150 divided by 25. So we could replace these with a 6 millifarad capacitor. So let's draw that circuit. No change here. This is still our 20 millifarad. And then it still branches off into this parallel combination, but we replace the 10 and the 15 with a single 6 millifarad. Of course, on the other branch, we still have this 24 millifarad. There's our 8 millifarad. Now this is easy. We can combine the 6 and the 24. The reason I say that's easy is because for capacitors in parallel, we just add the values together. So let's see, we can simplify the circuit even more. 20 millifarads, 30 millifarads in series with each other, and all that in parallel with an 8 millifarad. So again, we've got to apply this rule for series where we take the product over the sum. So this is going to be 600 divided by 50, 60 over 5, that gives us 12. So we can say this is like having a 12 millifarad in parallel with an 8 millifarad. And of course, that just gives us a single equivalent value of 20 millifarads. Boy. So let's put this equivalent value as the bottom line in our chart. And then let's just list all the other values. Okay, so we're going to assume these are all millifarads. So what do we have? We've got a the 20, the 10, the 15, 20, the 10, the 15, the 24, and the 8. Well, I guess I can draw that a little neater, can I? 20, 10, 15, 24. So the voltage across the whole equivalent combination is 60 volts. We find charge by multiplying capacitance and voltage together. This gives us 1,200 coulombs. So there's 1,200 coulombs in total. All right, now that gets divided up. Some of that is on the 8 millifarads, and the other is on the 12 millifarads. So let's see. Oh, and the electric potential here goes from 60 to 0, right? So not only is there 60 volts across the whole equivalent value, 60 to 0, but that 60 volts is the voltage across the 8 millifarad capacitor alone. So this must have 480. All right, so that means if this is 480, oh, and what I really mean is millicoulombs, right? So we'll just write here, this is implied to be millicoulombs. All I have to do is subtract the 480 from the 1200, and that's the amount of charge on this equivalent capacitance. So what is 1200 minus 480? That would give us, is my math right? 720? Sure. Okay, so let's go back a step here. This has 480 millicoulombs. These plates that I've just highlighted, we could think of those as these plates. And then charge by induction means that we're going to have 720 millicoulombs on each of these capacitors, right? So this one is this value here. Okay, so 720 millicoulombs. And that takes us back a step to here. 720 millicoulombs, 480 millicoulombs, and then this 720 millicoulombs is shared by these two capacitors. Now, we can find, we already know we're calling the electric potential here 60 volt, and down here 0. So I guess we can find what's the electric potential at this point. Okay, so if we're trying to find voltage, we divide charge by capacitance. So if I divide 720 by 20, that gives me 36 volts. So the potential difference at this point has to be 36 volts less than 60, which gives us a value of 24 volts. So there's 24 volts across this capacitor, there's 24 volts across this capacitor. So 24 volts. That means there's 576 millicoulombs on this capacitor. And if I subtract 576 from 720, you get 144. So this equivalent capacitance has 144 millicoulombs. Now we go back a step to here. 480 millicoulombs, 720 millicoulombs, 60 volt, 0 volt, 24 volt, 576 millicoulombs, and then this whole charge by induction conversation, this 144 millicoulombs is the charge on both of these capacitors. Remember, these are values in millicoulombs. So, if we, again, just use our equation, QVC, trying to solve for potential difference is a matter of dividing the charge on any particular capacitor by the capacitance of that particular capacitor. So we divide 144 by 10 and we get 14.4. We divide 144 by 15 and we get 9.6. I remember that's the answer we were looking for. If we can find the potential difference across the 15 millifarad capacitor, we have found the value of Vxy. Thanks for watching.